Being recorded.
Apparently the recording just started. So welcome everybody. I'm just going to do an informal overview of SCEV, i.e. scalar evolution. This talk, just to be upfront, is from memory and sort of I took some notes last night to make sure I remembered to say some of the key things, but this is not a formal presentation. There may be errors as I go through. If I say something doesn't sound quite right, please stop me and ask a question. That's totally fine. This is more of a structured discussion than it is a formal prepared talk. I wanted to start off with sort of a really basic notion of what scalar evolution can do in LLVM today, sort of what role it fills. Scalar evolution is a framework for asking questions about induction variables, is really what it comes down to fundamentally. And then there's a couple of things built on top of that for asking about the way induction variables behave in loops when those two are sometimes slightly different. SCEV is a layer that is built on top of the LLVM loop info infrastructure. So everything sort of that you know about loops continues to apply. SCEV is simply a way to, given a loop and a particular value for an induction variable, ask properties of that induction variable in a transformation that wants to do some form of loop transformation. To sort of give you a sense of some of the things that SCEV can do for you, take a look at our little example up here at the top, which is simply, a really simple loop that runs from 0 to n, and adds up that series. Some of the different queries that SCEV supports is you can ask properties of, and just as a side note, this is of course C code. In reality, SCEV works over LLVM. I use C just for ease of understanding and discussion. Also keep in mind that these results are me going, what would the answer be if I ran this, not having actually done so. So there's possibility of subtle errors here. First one though is simply asking properties of a SCEV, of a particular value. So in this case, it's what is the value of I? And what SCEV would tell me in this case is it would tell me that I have a add recurrence that actually starts at 0 and adds 1 on every iteration. And because this is C and we know that there's no signed overflow, we know that the add recurrence is both no signed wrap and no wrap, which I'll come to in a few minutes. The next type of information SCEV can give us is given a particular loop exit block, in this case the latch block of the loop, we can ask SCEV what the exit count of this loop is. An exit count in these terms is the number of times the back edge will run before the loop exits. And looking at that, that might be n-1. I might have typoed there when I wrote it out. The next piece of infrastructure SCEV has is for computing the value of sort of values and SCEVs defined inside of a loop at an outer scope. So you can, for a value that is defined inside of, in a loop, you can ask sort of SCEV, what is the value of that expression after the loop exits? And if it can find one, it will give you a closed form solution for what that value is. That's really useful for eliminating exits, or eliminating uses of values defined in loops as an example. It's also very useful for allowing us to kill many simple loop constructs entirely and replace them with closed form solutions. The next two types of information SCEV can give are probably the most useful, or at least the most widely used in practice. The first one is you can ask SCEV about the loop disposition of a value. Loop disposition, just for context, is this value defined in the loop? Is it invariant in the loop? There's a subtlety here we'll get to when we come back to this in detail, but that's a useful property. The next one is the really useful one, though. There's an entire family of utility functions on SCEV for asking properties of SCEVs or relationships between SCEVs. And those things that are trying to eliminate use values are built on top of that query infrastructure. So that's actually probably the most single common use of SCEV we'll see. But that's sort of a quick overview, just to give you a quick idea of some of the things that SCEV can tell you about a loop, and some of the questions you might think to ask. Next, we'll go through sort of a little bit more detail as to how SCEV does that, and then those interfaces in a bit more detail. Any questions on sort of the overview before I move on? Okay. So in terms of SCEV's internal representation, or so that is, what is a SCEV? Scalar evolution is the interface for returning a symbolic description of a computation. SCEV is that symbolic representation. SCEVs can be used to model today 2's complement integer types and pointer types. Note that there is no representation in SCEV for floating point types or for abstract integers, that is, not machine width 2's complement semantics. The set of nodes in a SCEV expression is actually very limited. You have SCEV unknown, which is simply a marker for something that SCEV doesn't understand. It contains a pointer to the value that defines that expression, and that's it. You have could not compute, which is SCEV says, I don't know the answer to this. Note that there's a subtlety here because there's a limitation in what SCEV can express. We'll get to it in a few moments around finite versus infinite values. And could not compute means both I didn't know how to compute this, and there's no representable result for this query. And you can't distinguish those two, unfortunately. Then we have the standard cast. We have a very limited set of arithmetic operations. We have add, we have sub, and we have unsigned divide. Note that there is no signed divide. And then we have the min-max expressions of both signed and unsigned varieties, and we have addrex. Addrex, or add recurrences, are really the key point of SCEV. When we went back to our little example above, sort of the ability to find that we have an induction variable that has a known step and a known start, and to analyze properties of that induction variable, that's what SCEV exists to do. The rest of the nodes basically exist to allow you to describe expressions that might result in addrex. The one opportunity for generalization that we have not taken is you could, for instance, have a div rec or a shift rec, or other types of recurrences that were symbolically described. There are loop examples where having such a thing would be potentially useful. SCEV currently does not represent them, and there's a trade-off between generality and complexity of implementation that we've generally defaulted to simpler concepts and implementation up till now. My personal view is we might be on the edge of reevaluating that in the next couple of years, but this is what it is today. A couple of properties here that are sort of useful to know. The first one is really mostly a warning, which is it's unusual to actually get a pointer type SCEV back from scalar evolution. If you have a data layout defined, then most of the time what you will get is you will get a integer typed result of the same width as the pointer type. However, this is not always true if the code you're running on doesn't have a data layout defined. You will get back pointer types. I note this mostly because it is very easy to write out a set of tests that exhaustively cover a transform and never see a pointer type SCEV, check in a change, and then have the build bots break because there's somebody running in one of the build bots that doesn't have a data layout defined. I point that one out because I personally have been bitten by that one multiple times, so I want to give a warning as to, a gotcha and a thing to watch for. So SCEVs are constructed by calling sort of get SCEV on scalar evolution given a value, and SCEVs are canonicalized at construction, so that if I have two values that represent the same underlying expression, the resulting SCEV should be pointer equal. Now, the pointer equal here is a bit of a subtlety, because there's no guarantee that we will prove two values equivalent if they are in fact equivalent. The only guarantee exists is that if the two SCEVs are pointer equal, then the two values expressions defined by the value are equivalent. The implementation note that's sort of really important to note here is that this canonicalization at construction is a source, is basically where the majority of the complexity in SCEV is. And because we canonicalize at construction, frequently when you're looking to get a better SCEV expression, that is a more reduced or more optimal one, the place you need to look in the implementation is the construction path for that SCEV. Unfortunately, that also means it can be somewhat fragile to write tests for SCEV canonicalization and sort of the optimization of SCEVs, essentially. When we get to the end, I have some ideas as to how we might change that, but for the moment, it's just important to note that that is how things work today. The other point here, and this is one that came up fairly recently and we got burnt by because, even I hadn't known this, is it is not legal to speculatively construct a SCEV. You can construct it from a value, but you can't, for instance, construct a add SCEV with an arbitrary set of flags unless those flags are actually valid in the current IR for the expression. The way SCEV handles flags today is problematic in multiple respects. We'll touch on that briefly towards the end. But since we're talking about SCEV construction here, I did want to give a quick warning just so folks were aware of that going forward.
One question there.
Mm-hmm.
There is a get minus SCEV, which is often used. I know there's a use in poly, and I've seen it otherwise away to get a base pointer out of from a subscript, array subscript. Is that illegal as well? Because it's not necessary that the minus SCEV expression exists.
So there is no minus SCEV, but there is a subtract SCEV. And the answer is that a problematic speculative construction? My honest answer is I'm not sure. I don't think so because it appears to work and it's widely used. The argument on why it's fine is there's no flag set there, so it's probably okay, but the current state of the flag logic in SCEV is it's observably correct most of the time, but there's no clearly stated invariance, and we keep getting bitten by them. That's unfortunately the truth as I know it right now.
I was referring to Scala evolution has a method get minus SCEV, which creates a plus negative expression. I've seen that used multiple times.
I would have to check and open the code real fast, but I don't believe that sets any flags on the resulting add, and thus it's probably okay.
It has a parameter for flags, which is flag any ref by default.
Then, so flag any means no flags.
Yes.
So then it's probably okay. I will have to take a closer look at that when we get done. That might be a good thing to drill into in some code at the end of sort of the discussion here.
Thank you.
But when you said it's probably okay, what symptoms would you see if it isn't okay? I mean, it's just going to be, I'm assuming,
a horrible, nasty miscompile.
Okay. Please. Okay. So you would, yeah, you would know pretty quick if it's you're doing something that's not you're not supposed to.
Well, yes and no. So one of the cases of misuse of SCEV's reasoning about flags that we fixed recently in LFTR had been present in LLVM for, I think, 8 years, and had been a mostly silent set of miscompiles until we made sort of CVP, or correlated value propagation, better about inferring NSW flags on ads, which turned out to be just enough to make what was previously a very rare miscompile much more frequent, and we had to go track it down and fix it before we could actually enable that functionality in CVP.
Okay, so when you say miscompile, you mean LLVM compiling user code, not building LLVM itself?
Correct.
Okay. Okay.
So the handling of flags is one of the areas I think we have to change. There's just no clear consensus as to what the right fix is just yet. Note that there's interactions here with things like freeze and, the fact that our undef and poison semantics are iffy to start with, and all of the interacting problems there. So let's see. So moving on beyond sort of basic SCEV queries, get SCEV at scope I basically already described. It gives you a way to ask a property of a value defined in a loop outside of a loop and to sort of see if there's a closed form solution for it. One subtlety just to note is that this is true for everywhere the value is defined. There can, of course, be locations in the outer loop where that value isn't defined by dominance, and you have to be aware of availability when sort of reasoning about what the value of the expression is. But this is just a classic optimizer gotcha. It's not really a SCEV-specific thing. The next sort of major class of infrastructure, which, to be honest, we sort of underuse, is SCEV has the ability to reason about the exit count of particular loop exits, and as a result, for many loops with either singular or multiple exits. The term that I've started using for this is to refer to an exit that SCEV can give me an exit count for as an analyzable exit and other exits as a non-analyzable exit. That's solely my terminology. It's not something that's standard in any way. What an exit count is the number of times the package is taken before a particular event occurs. SCEV can give us a precise exit count for any particular, or may be able to give us an exit count for any particular exit. One important subtlety here is that the exit count is only precise if that particular exit is the exit that is taken from the loop. So the most important implication of that is if the loop contains an exceptional exit, the exit counts do not model exceptional exits, and that will not be reflected in the reported package taken count for the loop, for instance. That's sort of the most important implication. In addition to the precise exit count, we also have the notion of a maximum exit count, which is a conservative constant approximation of the true max. We don't actually have a symbolic max today. There's some use cases I've been looking at recently where that would be very useful. I won't be surprised if we end up with one in the somewhat near future. But at the moment, the only form of upper bound we have on an exit count is in form of a constant expression. So as a result, it can sometimes be a very conservative upper bound. One subtlety that comes up when you get into multi-exit loops is it may be that you have loop exits that are provably never taken. So the correct exit count for that exit is going to be infinite, or at least larger than the exit count of all other exits. And we don't have a good way to describe that today in SCEV. What happens in practice is you get a SCEV could not compute, which is unfortunate because that's a case where we've generally done all of the analysis necessary to prove that exit is never taken. And then SCEV throws away the result and you can't query that in a useful way. It's sort of a limitation of the current infrastructure. In terms of the exit count computation, I'm not going to get into the details. It understands all the closed forms expressions. It also has a small brute force evaluator that will evaluate up to, I think it is 100 loop iterations. So even for loops that don't have closed form solutions, or sorry, I should say known closed form solutions, if they're short, SCEV will almost always give you an exact exit count, provided that the exit isn't data dependent or something. The other set of things built on top of this is there's helpers for asking properties of loops as opposed to individual loop exits. And there's some helpers for figuring out whether the trip count information we have is sufficient to either give us a small constant trip count, a small bound on the trip count, or to know that the trip count has a minimum multiple for instance, for vectorization or unrolling. Those sort of small trip count and multiple routines are probably actually the most heavily used infrastructure around trip counts, but trip count or exit counts in general are a very powerful construct that can be used by a lot of transformations. Questions on that before I move on?
I have a question on the conservative approximation of exit counts for exit that end up not being taken. So before you say that SCEV is only precise or able to tell you what the exit count of an exit is if that exit is taken. So if the exit is not taken, you say that it should be larger than any other count for every exit that is taken or infinite. How do you use that? I don't quite understand how SCEV make any computation for things that are not taken at all.
So let me go up and make my loop up here slightly more complicated just for ease of explanation. So here I just added an extra exit to this loop. And this time I said if I greater than m, return -1, just as a toy example. So the key thing now is I have two exits from this loop, one in terms of n, one in terms of m. Both of these exits will have analyzable exit counts because there's closed form solutions for if this exit were the one to be taken, what would the value of I be at the point, or what would the trip count be, or sorry, what would the back edge taken count be at the point that exit was taken? In this particular example, we have no knowledge of whether n or m is what the ordering is. But if, for instance, above the loop, we had something like n less than m, then we might be able to prove that one exit is never taken and that m is strictly greater than n. Does that make sense?
So in that case, SCEV will tell you that the exit count for the branch that you added inside the loop will be infinite?
So remember, there's no representation of infinite. I'm saying that that would be a nice thing to have, but today it would simply tell you could not compute if that's sort of the best it could come up with. So today, what you'd probably get is you'd get the exit count of the latch would be n, the exit count of the early exit would be m, the exit count of the loop would be the umin of n m, and then if SCEV noticed the assume, it might simplify this expression, the umin, back to simply n. So this is what you'd most likely get today. Note that this value, if SCEV is able to prove sort of that n is actually the exit, could be any value greater than n.
So I guess there is no way to, there is no easy way to ask the question, is this exit never taken?
So today, the way to do that is with the predicate infrastructure, the checking query infrastructure. So you can ask, you can say, give me the exit count of this loop, or sorry, of this latch. Give me the exit count of the loop. Is the exit count of this exit known to be greater than the exit count of the loop? That is an exit that is never taken.
Yeah. Okay.
And that is a transformation we do in var simplify, though only recently. I added that in the last couple of months. The use of exit counts had been somewhat limited up until recently.
I see. Okay. So that makes sense to me. There is a way, although it would be nice to have just a kind of like utility function that does exactly what you say.
Yep. So there's an efficiency reason not to, because you frequently want to do this for all loop exits, and you don't want to have, well, you know what, never mind. No, actually, you're completely right. Having that utility function would be useful, and there is no efficiency concern. So yeah, if you want to propose a patch for that, I'd happily review it.
Mm-hmm.
So some of the most useful queries that we end up asking is known predicate allows you to ask a generic question about any two SCEVs and the relationship between them. There's an entire family of query routines like is known non-zero, is known positive, et cetera, et cetera, et cetera. Basically all the things you're used to from value tracking, but as implemented over SCEVs. And then the other family that are essentially subsets of the former, but are really useful primitives on their own right for other transforms, so I want to call these out, is you can check to see whether a predicate is known on entry to a loop and on the back edge of a loop. The two of these together allow you to do inductive style proofs, and frequently, if you can prove one or the other, you can simplify an expression into something loop invariant. So for instance, that's the fundamental basis that like monotonic predicate and a lot of our make loop invariant expression stuff is all based on. But these are generally useful predicates for many loop transformations because like for vectorization, for instance, knowing whether something is true on entry to the loop is really useful. It's worth noting that particularly the entry form actually goes and explores control flow up above the loop, and will try to find evidence that the predicate you've queried is in fact true. Okay, so the next one is loop disposition, invariance, and the dominates routines. These are mostly used internal to SCEV, but have a few external consumers. the basic notion of loop disposition is it gives you an indication of whether the value that you're looking at is potentially loop invariant. Now, the potentially loop invariant piece here is a bit subtle because all it says is that the symbolic expression could be computed outside of the loop. It does not say that the value that you use to get that symbolic expression is outside the loop. And that is an important distinction. It's a distinction that trips a lot of people up, including myself multiple times. The main thing to be aware of there is if you want to do a transformation that needs to use a value, which is loop invariant, and you have a SCEV, which is loop invariant, you have to use the SCEV expander to generate a potentially new value outside of the loop to compute that expression. That's sort of the key warning takeaway from sort of that difference between is a SCEV invariant or is a value invariant. The dominance infrastructure is built on the same basic notion, which is, you know, given a expression that could be loop invariant, it dominates things inside the loop, for instance. It's all implemented together. Let's see, let me do a time check. So
let me ask a question about what you said about the difference between SCEV, whether the SCEV is invariant, the value is invariant. So let's say you have a value inside the loop, and you build a SCEV from that value. And then you ask whether that SCEV is loop invariant. And the answer is yes, it's invariant. So you're going to recompute that value outside of the loop. So you say that you have to use the SCEV expander rather than using the original value that you used to build the SCEV. Is that the correct interpretation of what you say?
Correct. In the simplest case, it might be that you can simply hoist that value out of the loop. But note that because SCEV heavily canonicalizes at construction, it might be the thing you ask a question of is a non-trivial phi cycle. And the symbolic expression that phi cycle takes has a known value on all iterations of the loop for some reason. So the rewrite to produce the symbolic invariant value, or sorry, I said that backwards. The rewrite to produce the invariant value as opposed to the invariant SCEV might be quite complicated, and that's what SCEV expander does for you. Does that make sense?
I got it. Yeah, it makes sense. It may be that maybe the file structure is not even available outside of the loop, right? So.
And it may very well not be. That's what SCEV expander does. Is it provides infrastructure for making things available. Right. We'll touch on SCEV expander in a few moments, just because there's some gotchas there.
Thank you.
The other sort of infrastructure that SCEV provides that's useful to know about is you can ask properties of, you know, the symbolic expression, which is a SCEV, very much analogous to known bits and to range information. That can be sometimes useful for implementing, you know, an inf-combine-like transform over SCEV. We, in general, don't like to duplicate stuff from inf-combine, but every once in a while we'll hit some critical transform where SCEV, because it has the closed form solutions for everything, can figure out a much tighter range than, you know, known bits can. And the infrastructure does exist to query that information and use it in sort of other transforms. There's also support for delinearization. I'll just note I have never personally used the support, so I do not know how effective it is. From some of the reports that have been mentioned at previous sort of working group sessions, it sounds like it might not be as effective as it could be, but there is existing support that exists in SCEV today for that. The next thing I'll mention, and unfortunately this is something I don't have direct experience with, so I'm basically reading the comments in the code and repeating them, is predicated scalar evolution is a means for constructing a set of SCEVs subject to some speculative assumptions. My rough understanding is the use case for this is you're doing some form of code versioning, and you're asking, after I version this loop subject to this predicate, what properties hold within this loop? One of the things I don't know is whether it's legal to use this in a purely speculative manner as opposed to committing to the versioning. It's just a subtlety I don't know the answer to. There's a whole class hierarchy of the types of predicates, i.e. Sort of assumptions you can form. Looking at the code, my impression is this could probably be unified with, the interface for the query logic. The notion of a predicate is probably one that could be reused in other places in SCEV, but the practical reality is I don't have much experience with this code. I don't know what its gotchas are. So I'll just mention it in passing, and if anyone else knows more about it and wants to share some at the end, that would be useful. Okay, so that's everything in terms of a SCEV overview in the infrastructure and what sort of queries things it provides. The next section is going into a bit of debugging and sort of some of the known problems in SCEV today. Does anyone have questions before I dive into that next piece, though?
I have a quick question about the fact that you mentioned there's no support for signed division in SCEV. Is there a particular reason for that?
So there's two answers. The first one is no one's added it. The second one is there is a strong interest in having the fewest possible nodes we can in SCEV. And this is just implementation complexity. We don't want to add a new sort of node freely. It's a very high cost exercise. So whenever there's a proposal to add a new node type, it has to be fairly heavily justified as being worthwhile. Most of the cases that have come up related to signed div, you can frequently prove that a UDiv is an equivalent in that case, and thus it's not a necessary construct. If you have examples where signed divs are heavily used in induction variable computations, share some examples and make a proposal.
Okay. Okay, just wanted to double check to see what the motive is. Okay.
Just as a side note, Poly kind of emulates signed division by kind of looking at whether there are any unknown SCEV values and whether that's a division and handles it on its own. It's not nice code, so I was always thinking about, for a long time, thinking about using adding an SDiv node to scalar evolution to toward this workaround in Poly. Another question, I noticed there's also no conditional. So if some predicate evaluates when, then this value, otherwise that value. Is there a reason not to use that? Is it again the justification part?
So I think the justification piece. Whenever you add, a select node, you've got recurrence whenever you have potentially cyclic structures, you have challenges there. We already have potentially cyclic structures, but it's just one more thing we'd have to think through. The biggest reason we're not adding more to SCEV is that in practical terms, the people working at it, I think, are at about our limit as to what we can understand. The best example I have of that is the fact that everybody understands that our current flag handling is broken, but none of us really know how to fix it. The other thing is we don't really have a SCEV maintainer at the moment. I'm probably the closest we have at the moment because I've been doing some things that have involved SCEV and I'm current enough on it to be able to mostly review things. But the folks we'd had who'd been actively working on SCEV had moved on to other roles, and there's no one who is, you know, frequently committing to SCEV as their primary activity. Okay, so I want to give a little bit of a flavor of how to debug and think about sort of SCEV issues. And what are some of the known gotchas to watch out for, sort of known weaknesses in the infrastructure? The first one, and it's a really simple one, is the old pass manager has the analysis pass mechanism. Looking at SCEV's analysis results for a loop is fairly simple. You just pass -analyze -scalar evolution, and you can optionally turn off the individual instruction classification. That's mostly useful if what you're interested in is strip count computation, which is what I've been looking at mostly. One of the things I've found is it is frequently very, very useful when looking at a missed optimization at a higher level to take a step back and look at the underlying SCEVs and make sure that they look as I would expect. One of the things I have been finding as I pushed, for instance, some of the exit count computation use sort of base transforms is that SCEV has some odd gaps in what have been implemented and what hasn't. So that is that you get back could not computes in cases where there is an obviously computable answer. There are some really interesting expectations in SCEV about the IR it's analyzing having already been partially canonicalized by int_combine and simplify CFG. And one of the things that happened when we moved from the old pass manager to the new pass manager is some of the assumptions about canonicalizations don't actually hold anymore. So one simple example of this is if you had a loop exit, which was a branch on a constant. So that is, it was either taken or it was not taken, and it was a constant in the code. SCEV looked at that and said, that's an unanalyzable exit count. I don't know what to do with that. And your results for the loop would become uber conservative. So I highly recommend looking at the results of the SCEV analysis when you're looking at some higher level thing that is a property of the loop, because there might be something odd missing that's a simple fix. The current one I hit, just last week is it turns out SCEV's exit count logic only understands less than and greater than comparisons, equality, less than and greater than. It does not understand, for instance, a signed less or equal expression. And there's this nice comment in the code about how, other passes will have already canonicalized this away. And that's the type of subtle interaction that there's some sort of implicit expectations as to how canonical the IR is. And unfortunately, they're not well documented. My sort of general leaning here is to generalize in these cases where doing so is cheap. But as I said, sort of looking at the underlying analysis result is a very useful thing in terms of identifying the root cause of a missed optimization or a miscompile. The other thing, and this one I want to highlight and like emphasize and put in bold, and please, if you remember nothing else from this talk, if you're working on SCEV, please test SCEV. Don't test invar simplify. Don't test loop unrolling. Please, 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 please. We have a challenge today with SCEV where a lot of our test coverage is indirectly measured through transforms, which can make it sometimes very challenging to, like, when making a change in SCEV, figure out whether all of the transforms are, whether there is sufficient coverage, and when there is a change, is it a correct change? Please, please, please test SCEV, not the transforms on top of it. Okay, so a number of these sort of known gotchas I've already mentioned, so I won't go into those particular ones again. Let's see. Let me see which ones I've talked about. So let's talk about sort of SCEV expander. I mentioned SCEV expander earlier and sort of what its job is, which is to take an expression that SCEV has determined to be loop invariant and produce a value outside of the loop that computes that same symbolic expression. The invariance between get loop disposition and SCEV expander are not well asserted and well documented. The practical experience we've had with SCEV expander is that it's observably correct, but every time we start doing something that, pushes a lot more things through it, we find another gotcha bug. So my caution here is SCEV expander is as correct as the current code forces it to be. In particular, the handling of how we hoist expressions that may fault and trigger or trigger UB is questionable today. I think it's mostly okay because the only really form we handle is a UDiv, which, if you look at the node types we have in SCEV, should be the only variety that you can actually trigger UB as opposed to propagating poison and undef. But this is an area where if you start working in this, be aware there's going to be some, you got to wrap your head around some invariants. And in particular, those invariants involve the definition of poison and undef in tricky ways. The bits about sort of flags in general, as I think most everybody's probably aware, our definitions of undef and poison are evolving in ways to try to make them a little less error-prone in the IR. SCEV has its own approximation of those rules, and hopefully everything will evolve in a way that is observably bug-free, but, may not. We'll see. The basic thing about flags in SCEV is the flags on a SCEV expression are potentially mutated when any use of that SCEV expression is found to have those flags valid. What this ends up meaning is that the flags on the expression are valid for the current set of uses. One of the really tempting things that you have to be very careful of is adding a new use of a SCEV expression may require invalidation of both the flags on the SCEV and the flags in the underlying IR that you're adding the use to. I'm not really sure to say this is a SCEV issue or if it's our definition of poison issue, but it's a sort of thing to watch out for. Generally, if you're working with a SCEV, deleting a value, replacing a value are both very low-risk operations. But if you're adding a new use of a value, stop, think, check with other people. That's where dragons lie. Some other just simple gotchas, but like they come up on a regular basis. I mentioned the pointer type SCEVs if you don't have data layouts. Another one just to be aware of is because you're asking many of these questions in the context of a particular loop, if that loop is itself contained inside of a loop nest, you may find yourself doing transformations that aren't legal for the loop nest, even though the fact about the particular loop was valid. So the simplest example of that is you can have a single exiting block which exits multiple loops in a loop nest at once. And because of that, rewriting that exit, given an exit count from the outer loop, you may change the exit count of the inner loop in a way that's unsound. So that's just one to be cautious of, in that particularly the exit count queries, but other SCEV queries as well, are loop context dependent, and you have to be careful around nested loops. Another one that's a bit of a surprise is when you ask for particularly exit counts, you may end up with exit counts for the same loop of different underlying data widths. There's a utility for merging them into a umin expression of the widest necessary type, but if you implicitly assume that all of the exit counts for a loop share a data width, for instance, that's incorrect. Let's see, what other gotchas here? The expression size thing, this is mostly resolved, but every once in a while we do find a case where generating a SCEV for a relatively simple IR fragment results in a SCEV that is exponential in size of the IR. That was a major problem 2 or 3 years ago until somebody went through and sort of restructured how we handle those cases. I think it's mostly resolved at this point. Okay. With that, I'm basically done, which, given we're at the end of the hour, is a good thing. Any questions?
For people on the phone, you might be on mute. Please remember to unmute if you have questions. We don't seem to have any questions here in Toronto. But that was a very informative talk. Thank you very much.
Yeah. So I do want to end with just the same warning I gave at the beginning, which is this is a talk done mostly from memory. It is summarizing my understanding of things and is probably mostly correct, but there may be subtle mistakes through it. In particular, like when I give particular exit counts and things, don't be surprised if there's off by 1 bugs in what I wrote down, things of that nature. Please don't take anything in this as gospel if it disagrees with the code or the comments therein.
Fair enough. Thank you very much again. So we are at the top of the clock. Unless there's anything else from the audience, I'm going to end the meeting. Please.
Next meeting?
So the next meeting is going to be in 2 weeks. Just before the holidays on the 18th of December. And I'm looking for agenda items that people want to talk about. We can add them to the agenda. Please let me know.
We want to talk about where is the recording going to be posted.
So we'll have to take that offline. I don't think we have a place to put the recordings in yet.
No, I think you can probably either email the dev list and see, or if you want to narrow it, you can email just the foundation and see. Let them know that we recorded this and if they have a preference for where the recordings go.
Okay, I can send a note. But I'll probably won't email it because the attachment would be too.
No, I'm sorry. I didn't mean to email it to the list. I meant to email the list or the foundation to ask where to post it, where to update it.
Yeah. So we have the YouTube channel. I wouldn't be completely surprised if that's where we decide to put it, but maybe we want a separate channel for this type of thing instead.
Yeah, of course, this is a video. There's video as well as audio, right? So.
Yeah.
Yeah. Probably on the YouTube channel makes sense.
Okay. Anything else? All right. Thank you very much for joining, and talk to you next time.
Thank you.
Bye-bye.